with a variation in the passiveness. Okay, now let us see how your op amp will be working as differentiator. This lecture is about op amp working as a differentiator. Let us enter into this lecture now. The contents what we are going to learn in this one will be basic integration amplifier, basic differentiation amplifier, practical differentiation amplifier, input and output waveforms and its frequency response. So these contents we are going to see: basic differentiation amplifier, practical differentiation amplifier, input output waveforms and frequency response. So introduction. What is an differentiator? So here, as the name itself, it tells that this circuit performs some mathematical operations of differentiation. What kind of differentiation it does, we are supposed to see now. The name itself, it tells that it's a differentiator. Means what? It does some operations, mathematical operations, just like the differentiation. So what it does, that means that the output waveform is a derivative of the input waveform. Here the output waveform is a derivative of an input waveform, and this differentiator is most commonly used where it is used in the signal wave shaping, just like your integrators. It is used in the signal wave shaping to detect the high frequency components at the input signals. Differentiators are mainly used to differentiate or in order to identify the high frequency components which are present at the input signal which you supply at the Vin. And it is also used as a rate of change of detector in FM modulators. It is used for the FM radio signals. It is used for frequency modulation. It is used as what? For differentiators. It's one of the application, very important. It can be one of the objectives as any of the competitive exams. So it is used as a rate of change detector. Differentiators are used as a rate of change detectors where for the frequency modulations in the frequency radios, FM radios. There we will be using these differentiators in order to, why we are using the frequency, why we are using the differentiator in the frequency modulators, in order to detect that high frequency components which can cause the noise. So now it will differentiate that one and it will remove that one. So now we are going to use this differentiator as a rate of change detectors in the frequency modulators. So this is a basic differentiator circuit now. This is a basic differentiator circuit. You can see here now in the basic differentiator circuit, in the earlier one, if you remember the integrated circuit which was studied in the previous lecture, if you remember that one, in that one the resistor was over here and capacitor was connected here. These two will be interchanged. Resistor will be, earlier it was a R1 resistor, now that in place of resistor you should replace it with a capacitor, and the feedback in the integrator it was an capacitor, now that has been replaced with a resistor. So that's the main difference. Means what? You can say that your differentiator is exactly opposite to your integrator. Your differentiator is exactly opposite to what, ma? Integrator. And there is another resistor which is connected here, this RF resistor. Remember, in the integrator we do not have this RF over there. We do not have RF over there. But in the differentiators we are using this one in order to detect that those kind of signals. So now which are causing noises. It means that it can be used for what? High frequency components. So that's why these are the main two changes where you can which you can find out between integrator and the differentiator. In the integrator there was a resistor over here and capacitor here. Now those two are being interchanged, and if you interchange those two, resistor and capacitor, it becomes as an differentiator. Your integrator is going to become as an differentiator. So now let us enter into this circuit. You can see now the same thing. Your input signal is connected to an inverting terminal, and the current across this one is equal to IC, and the current flowing through this one equal to IM. Now the same entire the process of finding out the output. There also in the integrator we have found out what is the output and how that output is going to become an integration of the input. Here what you are going to find out, here also you are going to find out the output voltage. That output voltage has to be differentiation of your input voltage. You can see now your output has to be a derivative of your input voltage. You are doing a differentiation to the input voltage, then you get your output V out. So now let us enter into this one. your RL is a load resistor and this is a IF, a feedback resistor. The current through this one IB is equal to 0 and IB1 equal to 0 and IB2 equal to 0, because I have told earlier that since these two terminals are directly shorted, virtually connected, that's why, because of the virtual ground concept, the current wave voltage across this one V1 is going to become 0, and the current IB and IB1 and IB2 is going to become 0. Why? Because there is a high input impedance at the input terminals. Because of high input impedance at the input terminals, the bias currents IB1 and IB2 is equal to 0 and V1 is equal to 0. Why? Because here the due to the concept of virtual ground concept. So now try to apply the same concept of deriving or finding out what is a V2. So that's V2. How to find out the V2? Apply the Kirchhoff current law again. If you apply the Kirchhoff current law, what will be that? IC is equal to the current entering the node is IC, current leaving the node is IB2 and IF. So IC equal to IB2 plus IF. IC equal to IB2 plus IF. So now you will write that formula in the next slide. You can see it. Now expression for the output voltage V out. How to find out the expression for output voltage V out? Apply the Kirchhoff current law at this node V2. If you apply that one, you will get IC equal to IB plus IF. Since IB equal to 0 as per the high input impedance of the op amp, then this formula is being converted into IC equal to IF. Now you apply the concept of current and voltage relationship across this capacitor. If you apply that one, it's C1. So it is C1 d by dt, and what is the voltage here? It is formula, actually the formula is C dV by dt, but my voltage here is what? It is a potential difference between these two voltages. So it is current is starting from V1 and it is entering to V2. So V1 is greater than V2. So that's why I will take it as V in minus V2. So C1 d upon dt V in minus V2 is equal to, what is this one? That's the IF. IF equal to what? I need to find out IF. IF is what? Again, it's a potential difference between these two. So potential difference between what? V2 minus V0. V2 minus V0 upon this resistor RF. So it is V2 minus V0 upon the resistor RF. And because of the just now I told that because of the virtual ground concept, V1 is equal to 0. If V1 equal to 0 volts, therefore simultaneously V1 and V2 are same at the same virtual ground points. V1 is equal to 0 means V2 is also going to become 0. So V1 is equal to V2 equal to 0 volts by the concept of virtual ground. Therefore, what happens if you do some mathematical analysis by substituting that V1 and V2 as 0, you will be getting C1 into D V in up D V in by dt is equal to minus V out by RF. Now you extract the V out by doing simple cross multiplication over here. V out is equal to minus RF into C1 into dV in by dt. So this is my final equation which you have found out here. What is that? That is nothing else but it is regarding the output voltage of a differentiator. This is the most important one. It's the output voltage of a differentiator, that's V out equal to minus RF C1 d V in by dt. So thus we can say that output voltage V out is equal to RF into C1 times the negative value of this one, negative instantaneous rate of the change in the input voltage. dV by dt means what? It is a change in the voltage. It's the rate of change of input voltage. dV1 by dt is nothing else but it's the rate of change of input voltage. So therefore we can write it as, thus the output voltage V out is equal to the product of RF into C1, which is times of the rate of change of instantaneous, or it's a negative instantaneous rate of change of input voltage with respect to time. So this is how we found out the V out. So from this one we can say the differentiator performs the reverse operation of integration. The sine wave input will produce a cos wave output, or a triangular wave input will produce a square wave output. It's exactly similar to opposite of the integration, but it has some practical problems. Let us see what are the practical problems here. The gain of this circuit. What is the gain of this circuit? The gain of circuit is RF upon the impedance of that capacitor. RF upon impedance of this capacitor is a gain. The gain of the circuit RF upon XC1 increases with the increase in frequency at the rate of 20 dB per decade. This makes the circuit unstable. What is happening here? The gain is going to increase with increase in frequency. But actually what has to happen here, we have studied in the basics that the gain is going to decrease as the frequency increases. The gain is going to decrease as the frequency increases. That's the basic of op amp which you have studied. But what is happening here? In this differentiator, the gain of this particular differentiator is going to increase as the frequency increases at this rate. At the rate of what? 20 dB per decade, or else you can even notate it as 6 dB per octave. It can be 20 dB per decade or 6 dB per octave. This makes, because of this relationship, we can say that the circuit is unstable. And also we can see there is an input impedance. There is an input impedance XC1 which decreases with the increase frequency. So this is again another problem. Your input impedance is decreasing with the increase in frequency. So these are the different kinds of problems which we encounter in the differentiator. So that are supposed to be minimized or reduced. So what happens if the input impedance decreases with increase in frequency? The circuit is very sensitive to the high frequency noises. Whenever this condition happens, this makes the circuit very sensitive. Means what? Easily the high frequency noises can be inculcated at the input part. Whenever the input impedance decreases with the increase in frequency, there is a chance of inculcation or addition of high frequency noises at the input. So that's why this is another problem. The first problem is what? We have seen the first problem. The gain is going to increase with the increase in frequency. This is the first problem. The second problem is what? The input impedance is going to decrease. The input impedance is going to decrease with the increase in frequency. What happens if the input impedance, this is again another objective. What happens if the input impedance decreases with the increase in frequency? Because of that one, high frequency noises can get added into the input signal. So these are the two main problems. So now what happens? When you go for the after amplification, what happens? Already if any kind of noise is inculcated, after amplification, that noise also this noise completely override the differentiated output. So this is a major final problem which we get with the noise inculcation. Whenever the noises are inculcated because of the decrease in impedance at the increase in frequency, this noise will override our main output. Means the complete output is going to be changed. It means you are not going to get a correct output, you are going to get an erroneous output. The output is going to be an error output. So because of this one, both the stability and the high frequency noise problems can be corrected with the help of addition of two components, that's R1 and CF, which is shown in the next one. So see now, how to correct this one? We are going to add the two components R1 and CF. So see now. This R1, I was talking about this R1. This R1 and CF is been connected for the differentiator. Earlier we were not having, we are having only C and RF. Now we are connecting R1 and CF. Why we are connecting these two components R1 and CF? Because in order to overcome this all the problems which you have discussed, and in order to maintain the stability. In order to maintain the stability and also to overcome the high frequency noises. So now let us study about this one. It's the same circuit. The change is that we have connected a R1 series with the C1 and we have connected CF in parallel with the RF. So see now, I was talking to you many times in the class regarding how to increase the gain of amplifiers in different ECAD softwares, just like PSPAS which you are working right now. I have told you to increase, or I told you to check what could be the value of that particular resistor, or what could be the value of particular capacitor, which is going to have the greater influence on the output, which is going to see some changes in the output. So these are those values which are found out practically by doing the research. So whenever your R1 is equal to 82 ohms, whenever your CF is equal to 0.005 microfarad, at this particular value of CF and R1 only, at the particular value of CF and R1 only, the stability and high frequency noise problems can be eliminated. Stability and noise problems can be eliminated. So these are the values. If you put different values of this R1 and CF, probably you might not get the greater stability as you get at these two values. So that's why I asked you to do some kind of research and to note down all the values while doing the designing of an op amp. So designing of an op amp depends upon the values of the passive elements. These passive elements which are mostly acting as a compensators, which are acting as a compensating elements. So see, you can see everywhere all the values of resistors have been given, all the values of capacitors have been given. If you change these values, this particular practical differentiator is not going to work like that, as it has to work. Okay, I hope you understood what's the importance of doing that research and finding out what could be the value of each and every parameter. So these are the input and output waveforms which you have seen. If you are giving a sinusoidal waveform, you are going to get the cosine waveform. If you are giving an input, triggering an input wave as an square wave, you are going to this kind of waveforms. So these are the input and output waveforms. Now let us see the frequency responses. So see now, frequency response of an open loop gain. Open loop frequencies, this one, the gain is going to go on falling over here. It goes on. And this one you can see it's a closed loop response of a basic integrator. This one which you see, this is a closed loop integrators, basic integrator, and this one is regarding the practical integrator. What is actually happening in the basic, sorry, it's a differentiator now. It's not an integrator, it's a differentiator. This is regarding the basic differentiator. In the basic differentiator, what was happening? The gain was going on increasing. You can see now, gain has started from here and it has entered to this part, and there is no end for this one. I don't know where it is going to become the FC. Okay, it means your gain is going on increasing with the increase in the frequency. But when it comes to the practical differentiator, what is happening to the practical differentiator? The practical differentiator, it's increased over here. At one particular point, it is decreasing. It has touched the 0 dB. So that is the difference between the basic differentiator and practical differentiator. In order to overcome, how did we overcome these problems? With the help of these two parameters which we have talked about. This is the R1 and CF. So these are two parameters which are used to maintain the stability and minimize the high frequency noises. So now here, the frequency response, just like we have calculated FA in the integrator, we will be calculating now. In the frequency response, FA is a frequency at which the gain is going to be 0 dB. Your FA is what, ma? Your FA is a frequency, okay, this one. This will becomes now your FA. 0 dB is becoming over here. So this becomes your now the FA of your practical differentiator. So now the frequency FA is a frequency at which gain is 0 dB, and it is given by this formula. We know this formula, F equal to 1 by 2 pi F RC. Here R is equal to RF and C equal to C1. FC is the unity gain bandwidth of an op amp if F is some relative operating frequency. And this one we know what is FC here. Now FC, we are talking FC in terms of the first case. In terms of the first case, for the open loop op amp, this is FC. And from the frequency F to FB, the gain increases at the rate of 20 dB per decade. And after FB, the gain is decreasing at 20 dB per decade. You can see here now. From F to FB, what is happening here? From F to FB, from FA to this point, its gain is going on increasing, and right from here to here, what is happening here? From this part, you can see the notations here. Up to between, it is increasing 20 dB. The 20 dB gain is there from this point to this point. Now from here to here, what is happening? It's going on decreasing. You can see now it is a decrease of minus 20 dB per decade. Here it's an increase of plus 20 dB per decade. And this means that this 40 dB decade change in gain caused the R1C1 and RFCF combination. So how did we get this stability? Because of adding of this feedback components. R1 is the extra resistor which we have added, and again CF is extra capacitor which I have added. Because of this product of RC combinations, we have got this 40 dB per decade change. So now here you can see the gain limiting terms, how to limit the gain. We have limited the gain by using this formula. Whenever the value of R1, this product of R1 and C1 is going to become RF and CF, we can limit the gain. The R1, C1 and RF, CF helps to reduce significantly the effect of high frequency noises and offsets. So what we have done, whenever you have connected this both the parameters R1 and CF, because of this connection only, your circuit has become stable, your differentiator has become stable, and also it was in a position to reduce the effect of high frequency noise and the offsets. And also just now, as I told you, this R1 and C1, this R1 C1 circuit, this combination of the RC, it's not acting as an RC filter. It's acting as an filter to reduce or to overcome the noises. These two combination RF and CF and R1 and C1 are used for stability purpose in order to increase the stability and also to overcome the noises. So you can see now R1 C1 and RF CF are used for stability, thus by preventing the increase in the gain with frequency. Earlier in the basic differentiator, the gain was going on increasing with the increase in frequency. But here what is happening? The gain has been become 0 dB whenever you have made this combination of CF and RF, and also it has reduced the noises or offsets. So you can see now what is happening here. We have seen this FA is lesser than FB and FB is lesser than FC in this case. You can see now this is your FA, FB and FC. FA is less than FB, FB is less than FC. So for that one, what you have got, the values will be selected. For this band, the value has been selected, and FA is equal to 1 by 2 pi RF C1, FB equal to 1 by 2 pi RF CF, and that is equal to 2 pi R1 C1. Why is RF into CF is going to become R1 into C1? Why? Because we have told that, I have told here that at this condition, whenever this combination are equal, we are going to get this particular problem solved. So this is again the research part. They have known that whenever the combination of R and C, the product of these two are same, then only these noises are removed and also the gain is stabilized. So from this one we can say, that's why we have written here RF is equal to R1 into C1. So ultimately the input signal will be differentiated properly if the time period of the input signal is larger than or equal to this one. The time period of the signal also should be greater than RF into C1. Then only we can have a very good differentiation. The design guidelines. We are supposed to find out the design guidelines. PMR. I was talking about the design guidelines. What are the values? How to select the values of parameters or components? That is called as a design guideline. What are the design guidelines for the practical differentiator? If select the FA, which is equal to the highest frequency of the input signal to be differentiator. The FA should be selected such a way that FA value should be very highest frequency of the input signal, and assume the value of C1. What should be the value of C1? Your value of C1 should be always lesser than 1 microfarad. You can see now in the circuit. What's the value of C1? The value of C1 should be always lesser than 1 microfarad. These are the assumptions which you are supposed to make. These are the actually calculated values which have been known after doing some research. So assume the value of C1 that is less than 1 microfarad, and now calculate the value of RF. So now for the second one, select the value of FB equal to 20 times of FA. Already you are having some value of FA, then how to select the FB? FB should be 20 times of FA, and calculate the value of R1 and CF, so that ultimately you will get this equation. Ultimately, at whenever the R1 C1 is going to become equal to RF CF, then the stability and noises will be removed. So this is regarding all the diagrams which I have taken here are from the Ramakant Gaikwad book, and this is about how your circuit will be working as a differentiator, how your op amp is going to work as a differentiator. What is a differentiator here? Differentiator is a circuit which will be where the output waveform is a derivative of your input waveform. Differentiator is a circuit where your output waveform is a derivative of your input waveform. Okay, thank you.